Hello, community. So great that you're back. Nano Banana, what a beautiful image generation model. But you know what? Today we go the next step because we do have a research paper on equilibrium matching. Equilibrium matching is a glimpse into the future of image generation with AI. And you say, of course, because we're here at the channel Discover AI for the latest in AI research. Those are our two papers, University of Oxford, October 3rd, 2025, and MIT and Harvard University, October 2nd, 2025. And at first we have to understand the first paper, and then we will jump immediately to paper number 2. So here we go. Diffusion models and the manifold hypothesis that is connected now with adaptive geometry. And you say, yes, of course, no? Because if you look at the isotropic smoothing of the score function that identifies the manifold structure, you say, we have seen this before, of course. In my video just days ago, where we talked about the unified theory of agentic reasoning, I told you that this work here by Jakiw and Peking University, they have now a unified reasoning manifold framework for understanding the reasoning in LLMs. And I also showed you this is based on a representation entropy that connected here the information tier with the LLM geometry. This was done by Jakiw University. And of course, you remember that we talked about the real core in the understanding was this paper. This was the paper here from 2013 testing the manifold hypothesis. And this was the most important paper here, if you want, in AI, in image generation. And now what we understood in 2013 in mathematics, in pure 50 pages of pure mathematics about separable Hilbert spaces, now we implement in a code for the next image generator. So let's have a look. How does it play out? Now, if you're not familiar with manifold hypothesis, easy. It just tells us that we have high-dimensional data, 1000-dimensional vector spaces, and the images in the audio and the real-world dataset are concentrated on a lower-dimensional submanifold embedded within the ambient space. And this explains why our machine learning models can generalize despite the curse of dimensionality. Now, if we looked at diffusion models, it was rather easy. I have about a dozen videos on the diffusion model explaining them. So very short, generate samples from data by reversing a forward noising process that transforms data into noise via an SDA, and then approximate the score function with a nublar log PT, the density at the time through a score matching. And then we have a loss, and you are familiar with this. Now, the conjecture is now that the diffusion model excels because the smoothing adapts to the low-dimensional manifold structure, remember, assumed by the manifold hypothesis, allowing us, therefore, the interpolation along the manifold rather than the full ambient space. So computational, much simpler, but mathematical to prove, much more difficult. And if you want, here, there's some beautiful mathematical lemma for you to follow. Having understand paper number 1, let's move now to the main paper of this video. MIT and Harvard say now, okay, so what about, diffusion and flow matching models learn non-equilibrium dynamics, but what is the next step? And finally, a paper that is challenging. Absolutely love it. So, generative modeling with implicit energy-based models, and they call it equilibrium matching. Why? What's happening here? Now, let's take a step back, and you know what we have today are either flow matching or energy, so let's start with flow matching. Flow matching models learn to match a conditional velocity along a linear path connecting the noise and the image samples. And during the sampling, the flow matching starts from a pure Gaussian noise and iteratively denoises the current sample using a velocity predicted by a particular function f. This process is governed by differential equation framework in which the predicted velocity is treated here as the time derivative of the desired sampling path and integrated over the total length. And you know this because in this video we applied here the flow to the reinforcement learning methodology based on G-flow net architectures. So if you're still using GRPO or DPO, have a look at this video because now we have a new reinforcement learning methodology with flow reinforcement learning. But now there's the next step, equilibrium matching. It is simple. We are standing on the shoulders of giants. Equilibrium matching combines now the advantages we found in the energy-based model and in the flow-based model, and we build now something much more beautiful. If you take only one sentence, let it be this sentence. Equilibrium matching learns a time invariant gradient field that is compatible with an underlying energy function, eliminating the time, the noise conditioning, and fixed horizon integrators. Have a look at this. If we have a look at the different time slices here, the flow matching, you are familiar. So we have two, if you want, valleys down here now, a three-dimensional manifold, and everything is now pointing exactly the way we wanted it here with the flow matching. But equilibrium matching, look at this. So what is happening here? I was thinking, how can I explain this? I think the simplest way is here, the diffusion and the flow models are like a GPS, no? It gives you a precise turn-by-turn direction. If you are somewhere positioned, you have to have a defined start, of course. Then the system tells you, hey, take 5 steps north, 3 steps west, and you got it, no? So direction change at every single point in your journey. And what you do at the beginning, let's say if you're high up in the plateau, is different what you do near the end. So if you're approaching here the energy minimum. Now, EQM is like a static map. So we have here dynamic, static map, much more easier, much computational faster. A static map of slopes always guiding to stable spot, energy minimum, offering the freedom in the path choice. This is amazing, offering freedom in the path choice. If you want, it's like a magical compass, and you have given here a topographical map and a compass, and the model learns here, of course, AI model, a magical compass that always points downhill, and you have here the indicator. So this is now a static map. How beautiful. But how do we create this map? How do we create this compass in this new methodology? Well, it's simple, but there's a profound mathematical trick. But at first, let me try to explain it in a simplified version. To train now this model, we show that, let's start with a corrupted image. No, it's a mix between the real image, here the real picture, and some pure noise. You know, it's a mixture. And the model's job is to look at this and predict now the compass direction where the model has to go. You're familiar with this if we are here on a curved gradient. Now, most models are trained to predict the direction towards the real image. This is like learning the velocity to get there. And now the trick, quotation mark, is we do the exact opposite. And I will explain later why, but let's do this simple explanation first. So EQM trains the model to predict the direction away from the real and towards the noise. And it seems backward, I know, but believe me, this is the key. If we look at the energy surfaces in 3D, you will understand it immediately. So by learning now the uphill direction, the model implicitly defines here a landscape, maybe an energy landscape. So to generate an image, now we simply follow the compass in the reverse direction. We go downhill. Of course, we have to make the valleys flat, no? We need the compass to stop pointing anywhere if we are in the local deepest valley. Because if it would keep pointing in any other direction, we would just continue, we would overshoot and climb out of the other side. No, if we have here local or absolute minimum, we want to stay there. So this is where EQM introduces here another trick idea, a dimmer switch function called C of y. So if y equals 0, the image is pure noise. Y equal 1, the image is a pure real image, a real photo. And now the dimmer switch is designed in a way to be strong when the image is mostly noise. So if we are far away from the valley, somewhere up in the Austrian mountains, and smoothly dials down to 0 when the image is now pure data when we are down in the valley. So the most important rule is, if we are really down at the value, our C function equals to 0. Because this new methodology learns now a static landscape and a compass, the inference, our generating image task, is now so much easier, becomes incredibly flexible also, no? Because instead of just taking a step downhill, you can make it even faster. Because you know from theoretical physics that we have not only the normal gradient functions, but we have accelerated gradient with a momentum And maybe you know a Nesterov accelerated gradient here with having a momentum, and you can imagine here the acceleration. And also it avoids getting stuck here in these small local minimums, these small bumpy parts here in the energy landscape that we have to pause to go here to the local or absolute minimum. There's another benefit. You know what we can do in this new thing? We can just add the two compass directions together and follow a combined path. We don't have to retrain them all. We just can do here, just add the directions. And why is it possible? Because the main idea is we're just learning, the AI is learning an energy landscape. And adding the gradients is equivalent to adding the energy landscape. It is mathematically such an elegant solution. Please have a look at the paper. Read the paper yourself. You're gonna take some time. Or you're a genius and you understand it immediately. Congratulations. And it is real simple to implement. Whereas doing this with a diffusion model is absolutely complex and often requires a complete retraining effort. But you know what? With EQRM, it's a native feature. Isn't this beautiful? Okay. Again. The main idea, what is it? Equilibrium matching's core idea is to train a generative model to learn an uphill direction field that always points away from the valley downhill data. And by scaling this direction with a dimmer switch that turns off at pure data points, here down in the valley, it creates a stable energy landscape. It builds us here this beautiful energy landscape. And you might say, hey, but why is this method so easy? It sounds so simple, so trivial, so beautiful. Well, now part 2. There is a complete mathematical framework behind everything I just told you. But you know what? I give you the result. The result is the equilibrium matching after all the mathematics is theoretically guaranteed to learn this data manifold. You remember the manifold hypothesis we started with the video? And produce samples from this manifold using gradient descent. And equilibrium matching achieves here 1 point, never mind Farghly inception distance on the ImageNet, forget it. It outperforms existing diffusion and flow-based counterparts in the generation quality. Flow matching at its best. Have a look at this. But we want to be better. We go here to equilibrium matching. Therefore, here you have a GitHub, everything is available, update 2 or 4 days ago. Beautiful, we have an MIT license. Isn't this beautiful? You have all the files that you need. If you want to have a look at the paper, look at chapter number 2, where they explain the flow matching because they build upon this. Then switch over to the training of the equilibrium matching model. You will understand here this function CR that I told you that controls here the gradient magnitude. And finally, to learn here the explicit energy function, the complexity here, there is a simple function defined. But of course, you have to go to the appendix because there you have the complete analysis. And there the authors tell us, hey, we provide the mathematical justifications for equilibrium matching. And if you have a weekend that you say, I want to learn for 2 days straight, just pure mathematics, this is your paper. Okay, so you see, summary. There's a easy way to understand it, or if you really want to have a deep dive, if you understand why it is necessary to have a PhD in theoretical physics and mathematics, or maybe just in mathematics, those ideas are not easy to prove. You can have this idea, like this here, flipping here the direction. Target direction is not the difference, the exact opposite here of the FM velocity. Why? Now we understand it, no? Because if the data x is to be a low energy minimum, you are at the minimum. You can't go deeper, no? You have to go in the opposite direction. The gradient must point away from it towards the mountain, no? Towards the higher energy regions, like the noise epsilon. And by learning now this field, we create a landscape where the descending, the gradient here takes you from the high energy, the noise, to the low energy, to your data points. And then the magnitude controller here of the target gradient. If you want, this is the secret sauce. It's so easy. It's a knob that you can have different magnitudes, but it's really a simple scalar function that controls here the magnitude of the target gradient. And it only must satisfy one exceptional, if you want, boundary condition, C of 1 equals 0. So this ensures if you're down in the valley, the needle just stops. This is it. You have reached your goal. So this ensures that when the interpolated sample is pure data, the target gradient is 0. You achieved your goal. By training the model to match this, we explicitly teach it that the gradient of all data points should vanish. Beautiful. And now a sentence that broke my brain. Because there's a hidden information theory behind this sentence. Can you feel it? This forces the data manifold to become a set of local minima in the learned energy landscape. We started the video here with the manifold approximation and the manifold hypothesis and everything and reduced subspace interdimensionality, and now we build it in a particular way to become a set of local minima. This is mathematically non-trivial. This is, if you come from theoretical physics and you work in quantum field theory, non-trivial. But it is beautiful. So, with this objective, EQM learns a single time invariant, time invariant vector field, f of x, that acts here as the gradient of an implicit energy function, E of x, where the ground truth samples are the stable stationary points. Great, and here you have now the equilibrium matching. It's so easy. Look, it couldn't be easier. Fast, gorgeous, the next generation. Because inference is now a simple optimization problem that we know exactly how to solve. We have now the ultimate flexibility. Because since EQM learns here a gradient field, generating a sample is no longer about integrating here a velocity over a fixed path like we do today. It is simply about finding a minimum of the energy landscape. And this is a standard optimization problem. So beautiful. But if you made it to the end of the video, let's come back and let's put this here where it belongs. I told you at the beginning, now we have the flow models and we have the energy models. You know what? If we look now at this third idea, we suddenly understand that flow and energy are just two sides of the same coin, distinguished by whether the learned vector field is a conservative, a gradient field or not. But now we have a third perspective, and this third perspective will bridge those other two sides of the same coin. So you see, we can build now a unified perspective. And this unified perspective, EQM, could really inspire an entire new class of models that simply moves here between the two regimes, and you can decide when to use what. You don't have to build separate models. You don't have to train separate models. It's just three sides of the same coin in a higher dimensional mathematical space. Let me explain. Now, all the diffusion and flow-based models that we have, these are our current champions here for image quality. But we both understand that it's a non-equilibrium process, meaning that the rules of the movement, the velocity fields in a high-dimensional space, change at every single step, at every single time. And this rigidity leads now to constraint, fixed sampling step, predefined schedule, and more. It's the newer model, but it's complex. Our good old friend from hundreds of years ago, maybe a little bit incorrect, the energy-based models, now our EBMs. The master flexibility, good old friends, they learn here a timeless, static energy landscape where the data points are the valleys, low energy, what a surprise, and everything else is in the hill and the mountains and the high energy. To generate now a sample, you place a ball anywhere in this three-dimensional landscape and let it downhill via an optimization, our typical gradient descent. This is an equilibrium process. This is a non-equilibrium process. But, this is the big but here, all of this is highly unstable, difficult to train, and only full of problems. But if we understand now that there is a bridge function where we just take here the advantage here, the best parts of the diffusion and flow-based models, and everything that is good about energy-based model, and we build now the next generation, equilibrium matching. It is really kind of a revolutionary unification of these two, let's call it kingdoms. It proposes here a way, and a mathematical pure way, but I have not yet the time, I need a weekend to really understand the mathematics behind this, to build a generative model that learns a static energy landscape, like an EBM, but it is trained with the stability and the scalability of modern flow matching models. The best of both worlds. Absolutely. But you know what? We can unlock EPM's superpowers at scale because naturally EQM enables you tasks that are too complex for the diffusion or real complex and real time intensive, real expensive for the diffusion models to do for the training, such as the denoising partially corrupted images or inherent out-of-distribution detection and simple powerful compositional generation. Isn't this beautiful? Combine the best of both worlds. And maybe this is really a conceptual shift that might redefine how we approach generative sampling. So there you have it. 2 brand new studies. One, University of Oxford, Department of Statistics, October 3rd, and MIT and Harvard University, October 2nd, equilibrium matching. What a beautiful idea. I hope you enjoyed it. I hope I was able to communicate the beauty and the simplicity of these ideas, but also the complexity if you really want to publish this and you really want to code this, because you have to prove that all your assumptions are correct and you can build a mathematical construct that allows you to argue, I'm able to do this in the limit, or I can have a convergence of this time series. I can build here a time invariant gradient. I have my energy fields. Therefore, you need a lot of mathematics, a lot of theoretical physics. But if you are interested in this, you see, you can have everything from pure mathematics to theoretical physics. You can, if you understand why we are doing something, it is rather easy then to build the code and implement it. So, this was it for today. An outlook for the next image generation AI systems, and maybe they will use equilibrium matching. Subscribe, and I see you in my next video.